Welcome to our position paper dissemination workshop. My name is Christoph Grzeschik from the Task Force Digitalization. I'm the task force lead here from the Battery Secretariat. And yeah, I welcome you to this workshop. We are not only here to present the position paper that we have been writing in the last months in the Task Force Digitalization, but also in the other task forces here from Batteries Europe. And we would like to present to you the results, some key insights of this position paper, and then dive a little bit deeper into a discussion on how digitalization will actually affect the whole value chain and what are current advances and guidelines for the battery value chain in terms of digitalization. So let's have a short look on the agenda. So Maher, Chebbo, the task force chair, he's at Universe. He will present the position paper in the next 15 minutes, so you get a good overview of the findings and the general topics we will address also within the workshop. And then we will have a short talk by Simon Clark from SINTEF about common languages as a foundation for battery digitalization. Afterwards, we will have 10 minutes time to have a short Q&A session. Currently talking, would be great if you could mute your mic. Thank you. And then we can have some questions from your side for the two talks that we then had before, and then we will dive into the main part of the workshop, which is the panel discussion. We have three guests here from the industry and from the science side, and yeah, we will just be able to ask some questions. You will be able to bring in your ideas and discuss them, and yeah, then we should conclude the workshop around 10:55, and then we will have a short break. Following up, there's another workshop from the task force hybridization. So if you have the time and you're interested, you're welcome to join also this following workshop then. Okay, so much for the presentation of the agenda. And first, I would like Maher Chebbo, the task force chair, to present the position paper, and yeah, he will touch upon some of the central topics that will be then discussed further on. Just for you to notice, this meeting will be recorded. So the recording will be made available to you afterwards to all registered persons. And if you have any questions already that you would like to address to one of the two speakers, you can put them in the chat, and then we can discuss them during the Q&A session following. Okay, Maher, so
should I share my screen or just stay on your slide?
Okay, I have the slide set here.
Good.
Just
so I wanted to give a bit of highlight on the battery industry. So currently in the world, there is 300 battery gigafactories that have been announced, 50 in Europe. You hear sometimes other numbers, but there is a huge number of gigafactories producing batteries. And this is about 25% increase year on year. It's a lot of investments. And these investments are not only in building the real estate buildings and putting equipments, hardware, it's also a lot of investments in the digital part. Next slide. So there are two types of batteries, the EV batteries, and these ones today, what you find out in a car, and you have everything about the health, the prediction of the discharge of the battery, depending on the speed of the cars. So there have been very much sophistication in following the granularity of the state of the batteries in the EVs. And the other type is the stationary batteries, ESS. In the gigafactories, you could have the same technology, for example, LFP or lithium, which could be used for both of them, but you could have a different line of production for producing one versus the other. Now, when it comes to the stationary batteries, we are talking about a system where you need to have a battery management system on the packaged packs of batteries You need to also manage the relationship with the power conversion systems, with the ECS system, high voltage and high flexibility, the energy management system, and everything that happens behind the meter. So the stationary batteries could be used in power generation, for example, to help in managing the flexibility. They could be used as well at the level of the stabilizing the grid, but also they could be used with the renewables, and they could be used in any building in B2B or smaller batteries for B2C. Next one. Now, just get back, please. And now, when we speak about digitalization, we have decided in this task force to look at all the process that happens end to end in the manufacturing side. And second, the usage of the batteries. So when you are in the manufacturing, you are in the world of EPCs, so you build the gigafactory. Then you have the process manufacturing. You are in the world of operating the factory. And then when the batteries go out, whether they are in the cars or they are in stationary usage, this is where you need to keep track as well of the context in which the battery worked, and get a lot of return on experience. Today, this is very much a growing market. We still need a lot of return on experience on these batteries. And also because you need to recycle them, right? And this is going to be by directives, by European directives, with the obligation for recycling. Okay, so this is why you need. And so there are some topics that we have put in the position paper that you see here. Everything, but not an objective in itself, is the digital twin. If you don't have a mirror or a copy of the physical assets, it's very hard actually to predict how the assets, batteries, can behave. Second is everything around artificial intelligence. These are enabling technologies like the digital twin and the ontologies. We'll speak about that. And then everything around data spaces, the state of everything, state of health of the battery, state of end of life, state of safety, and so on. And cybersecurity. And what's important as well is, since a lot of people are saying, well, but the batteries are not that clean and so on, we need to follow the life cycle assessment. And the life cycle assessment is end to end, including the raw materials, including the process, for example, and the energy you use as well to produce the batteries. And then you need also to integrate with the rest of the energy system, ERP systems, energy with the ERP system supply chain. Okay, and the rest that you see here is about more standardization, all these practices in the plants. Next slide. So as I said in the position paper, we presented the current central aspects in the digitalization. And also we are providing the recommendations to say how we could be effective in making the digital enabling technologies and use cases be convergent with the industrial world across the value chain. Next one. So central topics that we address is to have a common infrastructure, data shapes, and ontologies. Why? Because we need to speak the same language. We need to get attributes, for example, provided for the materials and for every side of the batteries. Once we define all the schemas and the ontologies properly for the batteries, then we can compare apples with apples. We can establish some standards as well, and we are capable as well to develop on top of this more advanced intelligence, artificial intelligence, and more advanced models. So the advanced modeling, where we use a lot of physics, where we use a lot of domain of expertise of the batteries. This is why we need people who really have been observing, all the problems that could happen on batteries, observing as well the decreasing end of life, for example, of the battery. So these people are capable to model things that we could predict how the battery will behave. And digital twin and AI is all, enabling technologies. They are not an objective in itself. And the KPIs, at the end of the day, what counts for the users and for the market is the key performance indicators. So the state of something, as you do in any asset, where you have the asset health, where you have the asset performance management, and so on, These are things where the contractual, the ones who are, for example, the developer of battery projects, they are seeking after having a security in terms of signing contracts with commitments on these kind of key performance indicators. Next one. We got in the last week, actually, when we were presenting after the General Assembly, the next day, we were presenting this paper, questions also about the ontology. So this is quite complicated topic. So a lot of academies are working on it. A lot of digital companies also are working on defining for different kinds of assets. What are the objects, the links between the objects, the logical concept, everything that you would find as well in a digital twin, as well as the interoperability between the systems. Okay, so particularly here, interoperability between the system of the batteries, the system of the what happens behind the meter, a system with the power conversion. You have a lot of systems that are here heterogeneous, and you need to define also the interfaces among them. So we need to have a consistent vocabulary that at the end of the day, we bring some standardization on the market and we can compare apples with apples. Next one. So when we speak about data shapes and ontologies, there is also the importance of defining the resulting digital services. So once we have defined all the structure and we have defined all these attributes and the ontologies, then we can speak about the use cases that we could deliver, where we can leverage all the experience on the data or the machine learning or the domain of expertise on the batteries. But first of all, we need to define the attributes properly, and we need to have also common data space where you could also benchmark, for example, and compare the experiences that you have on the safety of the batteries, on the cybersecurity, on multiple things that could benefit actually at European wide. And we need then to interface as well when it comes to the ontologies. This is something, it's not only just for digitalization, it's also for the sustainability task force. This is also for the hybridization, and this is also for anything which is related to this topic. Next one. Now, the modeling is key. So if we are only talking about enabling technologies and we are only talking about digitalization with pure software engineers, we will not be capable to deliver valuable services. So this is why we need to have people who understand the chemicals, who understand the physics, understand that high-tech industry, and also people who are specialists in the energy and the integration with the electricity sector, for example. And these ones will develop the algorithm and the models. So we need them to have very easy modeling tools. There are some platforms that can help you very quickly to develop new models, okay? But these are only helping with tools, I would say. And we say here, we need to have these kind of tools, but you need to have also the brains and the double competencies that these people who know about the physics, chemicals, and know about electricity and electricity integration will bring in the game. So what we are saying is let's have a centralized repository of automated methodologies, and people could use it maybe in open source, have access to this centralized repository, and then based on this, develop very quickly the models that we need. Next one. Digital twin, as I said a couple of times, this is something which could be at the level of a spare part, but could be at the level as well of multiple spare parts, or it could be at the level of a battery, could be as well at the level of a factory, okay? So these digital twins are just reproducing permanently, continuously, they are reproducing the progress of these assets, the health of these assets. So everything is a mirror here, so that we could run all the predictive analytics, for example, to do asset health, asset performance management, and so on. So definitely this is an important technology we need to put in place. Next one. And I mentioned the importance of the key performance indicators. Once we have the anthologies, once we have the models defined and so on, then we can display with some dashboards and some analytics, we can display the status of everything about the battery, the safety, the cybersecurity, the level of charge and discharge, and what if scenarios as well. And also we can display, and this is very important, what's the end of life of the batteries and when we need to start recycling it or to replace it. Okay, that appeals. This is the resultant. These KPIs that are delivered out of SOX. These are the resultants of everything that we have done before. Next one. So what are our general recommendations is to identify the full digital landscape. Okay, this is quite broad. Digital is not IT, it's about business processes, right? So if you are in the factory manufacturing batteries, the business processes, you will find business processes on procurement, business processes on finance, on supply chain management, manufacturing execution system, quality. All of these need to integrate with the IoT as well and all the data we are collecting from the plant. We need to represent it also through digital twins, and we need to make advanced analytics that take the data from the ERP supply chain manufacturing systems, as well as the data from the assets themselves at the level of every sensor or every asset. And we have to do, yes, some experimental pilots, but these pilots, we are suffering a lot in Europe, and we are slowing down the process by having just pilots. So what we need is to have that as a part of a scaling up or part of a rollout as an initial phase, starting by a small scale, taking some learnings, and then continue by scaling up. Standardization in key. We need to participate in whatever mandate, for example, to find out standardization in interfacing. Standardization in some models, for example, standardization the way we calculate the life cycle assessment of carbon emissions. And then at the end, we need to assume the responsibility for data ownership. The big pain thing is that nobody is responsible for the data. So we need to say who is the owner of which kind of data, or who is the owner of which kind of process, which will generate, for example, data, right? And if we are talking about common data model or common data repository, and we need to have a common platform on which everybody would come, then here you might need to have an independent system operator, for example, to maintain all the data. For example, smart metering, you have like in some countries, a common platform where you have all the data coming there, but then you need to have an independent system operator for that. Next slide. So it's just a couple of graphics that we have drafted initially as well in the previous report. The integration, particularly of the stationary batteries with the rest of the electricity system, with the high voltage TSOs, medium to low voltage distribution system operators, the suppliers and power generators, and the behind the meter customers. So there is a lot of complexity, and this complexity should be done by all the stakeholders. And we need to have the customers accessing something very simple, accessing the procurement of the batteries in a simple way, but also developing projects where we install the batteries, for example, in a very simple way. So there's very complex. That means that the electricity stakeholders have to work as well with the battery stakeholders. Next one. One of the lighthouse projects we could have is how we can have the complexity done by all these stakeholders. And we have a simple platform, kind of Amazon of batteries, where you could have information about everything, all the characteristics in this simple way. Use maybe also natural language, for example, to say, okay, I need a battery that does this and that. And then you can have access not only to the characteristics of the batteries, but also you can have access to all the ecosystem around it, and be capable as well to make cost benefits assessments. A lot of these projects, for example, the batteries, are a bit stuck because people do not know how to calculate the benefits out of it. Next one. And I will leave you probably with this last slide. Of course, we are in a market where there is a lot of investments going on. Sometimes you see the 50 announced gigafactories in Europe or the 300 in the world, people underestimate in their budgets the digital part. And I have seen that myself actually on a couple of concrete examples where you could have an announcement for 1 billion of investment on a gigafactory that produces 10 gigawatt hour of battery. This is a bit the range of investment, creating 1,000 jobs, but the guys have forgot to put the budget for digitalization. So this is key, and this is what will help as well to replicate, to scale up. If you want to build another gigafactory, for example, for producing batteries, the digital will help you to collect all the data that you can replicate it in a more effective way. And certainly, one, it is in the users that digitalization is absolutely key. Whether it's in recycling, whether it's in the most performant way to use the batteries, and whether to develop the whole ecosystem as well when you are in the user side. Thank you.
Okay, thanks, Maher, for presenting the position paper. In case you didn't read the position paper yet, you can find it on the website batterieseurope.eu. There are also other position papers published now, for example, for sustainability, education and skills, or hybridization. You'll find also other documents there, like a strategic research and innovation agenda or a roadmap. So please check out the website in case you didn't do so yet. And again, you find all the position papers there. Okay, next up, it's Simon Clark. He's a senior researcher from batteries at SINTEF Norway, and he's working on digitalization, trying to bridge experiments and simulation. Yeah, like Maher already said, like in everyday life, systems do not interact properly unless there's a common language agreed upon, and same holds for digitalization here. And Simon will talk about some aspects concerning a common language set here for digitalization. And again, just write your questions in the chat, and we can address them later on in the Q&A session. Okay, Simon, floor is yours.
Great, thank you very much. It's a pleasure to be here. Yeah, as introduced already, I'm going to be discussing the battery interface ontology, which is a common language as a foundation for battery digitalization. And over the next 10 minutes, I'm going to briefly introduce the concept and then show one simple example that I hope will kind of whet your appetite and leave you wanting to learn more about how this can be applied in your own work. So please go to the next slide and click twice. So if we want to start dealing with the digitalization issue and how we can start bringing things together, we need to look at all the types of data that we have available. And if you click one more time, and especially in the battery field, this can be very diverse. It's not just normal scalar data. It's strings and integers and images and all sorts of heterogeneous things that we have to bring together. Click one more time. And structuring this can help, having common schemas and trying to adhere to common data models. But if we really want to get the value out of this, we need to be able to take the step from data to knowledge. And that means connecting our data to meaning. If you click one more time. And luckily, to do that, we don't have to reinvent the wheel, because if you were to start from scratch, this would be a Herculean task. But there exist already semantic technologies that specialize in linking data with meaning, and they're actually some of the technologies that are the foundation for the World Wide Web that we know and interact with today. I'll give you an example. If you go to the next slide. If you're searching for somebody today, either on Google or a social network, oftentimes you'll land at a page that kind of looks like this, where it has some nice human readable information, a picture, some information about where that person works. And this is, designed to be consumed by people. But what we don't see, what's shown on the next slide, if you click, is that this is actually just one node in a much larger graph that is linked to other sources of information. And on the one hand, this provides huge amounts of power to start linking information across different sources, finding the connections about things, inferring new information about how different nodes are connected. But the only way it works is if we have a common standardized language for describing resources in this graph. You can imagine if everybody used their own language or their own codes to describe this, it would quickly become totally unusable. But about 20 years ago, Google and Microsoft and a lot of the big search engines got together and started to standardize what we call RDF vocabularies for describing things in a linked data graph. And they came up with things that describe what people typically search. Like if we have a description of a person, that person has a name, maybe he has an address, he has an affiliation at some organization, some link to other people. And this has been extremely well developed for people, or for things that people like to search for, people and places and products and movies. But one thing that it has not really been well developed for, at least until recently, was scientific data and materials information. If you move to the next slide. So what we want to do is to take this same concept. Now, if you click to the next one, okay. What we want to do is, sorry, back one. What we want to do is take the same concept that has been used very effectively in social media and in search engines and apply it for batteries and battery data. We want to create a network of battery assets that we can use not only to share information and link data across different sources, but use that to infer new information and accelerate our design and discovery processes. If you can click to the next slide. So what do we need to do that? Well, you need three things. First, you need a system to identify resources uniquely. And we can build on a lot of web standards like URLs and URIs for doing that. Second, we need to develop a vocabulary of concepts that describes the type of information that we want to use. And third, we need to democratize access through the World Wide Web. And over the past 5 years or so, we have been focused on this center one, trying to develop a vocabulary of concepts that describes batteries and battery data in ways that adhere to World Wide Web and semantic web standards that can be used to share that information across different sources. So if you go to the next slide. I'm going to show you one simple example of how this can be applied, and even in this really simple embodiment, we can still use it to gain new information and link to other sources of data. So I'm going to show an example where we describe a coin cell, a battery coin cell, using semantic metadata from the battery interface ontology that's then linked to another source of information on the Wikidata database that can be queried by a person or a machine agent. You go to the next slide. So when we create semantic metadata to describe our resources, one of the easiest ways we can do that is through a format called JSON-LD, which is JSON for linked data. And in its most simple form, which is shown here, really you only need two things. The first is a link to a description of the ontology, which we provide here in the context, mapping some human readable labels to ontology terms in the graph. And we need something describing the type of thing that we are wanting to describe. And in this case, a battery expert will look at this and say, CR2032, that's an IEC code. I know that the C is a chemistry code and the R2032 means this is a coin cell with 20 millimeter diameter and 3.2 millimeter thickness. But the machine doesn't know that. And so the ontology provides us a way to encode that information in a way that the machine can understand and link to different sources. So if you go to the next slide. Oh yeah, and this is simple. It's easy, and this builds on existing standards that power the World Wide Web already. Okay, you go to the next one. There we go. So if you go into the context, what you'll see is something like this. It's basically a list of human readable labels linked to terms in the ontology that are machine readable on the right. If you click again, each of these labels, and one more time, please, each of these labels resolves to human readable documentation that describes what that resource is and provides links to other sources of information. One more time, please. And through the system of what we call internationalized reference identifiers, these IRIs, we can create persistent identifiers that are unique to describe resources and also are resolvable for humans through a web browser, for example. Okay, one more time. And the real power of these things is not necessarily describing the metadata itself, even though that's very helpful for experimental reproducibility and understanding what's been done. But the real power comes when you start to link to other sources of data where you can retrieve more information than is expressed in your metadata itself. So because in this example, our CR2032 cell is linked to the battery interface ontology, and the battery interface ontology is linked to other sources of information like Wikidata, we can do a query to get like, what's the diameter of a 2032 cell? And if you click again, the Wikidata API can return that information that is 20 millimeters. And we can get not only this kind of simple scalar information, but even heterogeneous and multimedia data. Like we can get an image of a 2032 cell if you click again. So the takeaway from this is even in that extremely simple description where we just point to the ontology and give it a 2032 CR2032 label, we're already able to link to other sources of information and pull related data that can help us in our search for new information. So to summarize, on the final slide, you can find more information with more complete and more exciting examples on the battery interface ontology documentation, which you can access either at that URL or through that QR code. And there we provide some other resources that will help you get started and learn how to apply this in your work. We also link to other large-scale ontology activities going on in Europe. The battery interface ontology is a domain of the EMMO, the Elementary Multi-Perspective Materials Ontology, which provides access to a larger set of domains and information from different research activities in Europe. So that's my time. Thank you very much for your attention. If you go to the next slide, I'd just like to thank the European Union for their funding, and especially the projects Big Map and the Battery 2030 Plus initiative for supporting this work. Thank you.
Okay, thank you, Simon, for those insights on a common language and how actually we can all tie these different branches of digitalization together, and how this is a fundamental key aspect. Now we have some short time for answering some questions. I've seen already that in the chat we have one from Peter Fischer. Maybe Peter, if you want to ask the question directly, or shall I read it?
Yeah, I mean, there are at the moment a lot of approaches to work on ontologies. You already mentioned that the battery interface ontology is part of the EMO ontology, but there are of course more ontologies. And how do you harmonize them? For example, with open energy ontology, I know there's also by INM in Germany a lithium battery material ontology. How do you harmonize all these, and that people don't start at zero, and that these ontologies grow together?
Yeah, that's an extremely good point. I think in ontology development, the problem is not always that that there aren't enough ontologies. It's that there are too many, and we're not reusing things that already exist. So as you point out, we're under the umbrella of EMMO, which seeks to try to address that problem by creating some kind of common standards that any ontology that's developed under the EMMO guidelines is interoperable with any other one. So you get kind of consistency within the EMMO universe, but then eventually you need to move to other universes or other top level ontologies. And we can do that on the one hand by adhering to semantic web standards that everything is reusing kind of common top level terms like RDFS and SCOS, and we try to link back to that whenever possible. It's also possible to make equivalences between different classes and different ontologies using same as relations. So if there's like a battery cell in our ontology and some other universe, there's another one, we can define equivalence between those two. But I think having some kind of consistency at the top level and trying to do those mappings at the top level is the best way to go about it.
I see here the danger that we have different areas because, for example, energy ontology is a wider umbrella, but also has, for example, batteries as part of it. And so it would be good to connect all these ontologies to get
absolutely
better interoperability. Okay.
Absolutely.
Okay. Is there another question from the audience? I don't see anything more in the chat currently.
I have a question.
Yeah, great.
Hi, Simon. I was wondering, okay, is this mainly for use with open source data, information that you're very much open and willing to provide, or could it be used also for some of the data, like, for example, you know, when we're recycling, the recyclers need certain information about what's in the actual battery, but that's not necessarily to be opened up to the entire world due to some sensitivities with IPR. So are we also talking about how to do that, or is it more open data?
Yeah, that's also a really good question. And the short answer is that you can use it for both open data and closed data. And the analogy that we draw is, at the end of the day, it's a language, right? It's a language that machines can understand for describing things. And just like in the languages we speak, like we're all speaking English here, so we can all understand each other, but you know, we choose what to say. You know, we say some things in public and we say some things in private, and it's the same kind of thing. You can use the ontology to describe resources if you want to publish them, but if you want to keep things closed, you just put that behind your own company firewall or your own company intranet, and you can use the same approaches without you know, having to make everything open.
Yeah, thank you very much. I guess this could take a lot longer discussion to understand the hows and the why and the exactly how you do this, but this is very much welcomed what you're doing. And this particular area of getting these ontologies to talk to each other as such, that's very important.
Okay, so the positive outlook is definitely there. We're speaking here all in English, exchanging our information, different systems all over the world, all over the places, working together. So I think there's also the positive outlook that this can work in digitalization, especially for batteries. So I would say we go further to the panel session. And yeah, we would like to dive a little bit deeper into the aspects and challenges and opportunities of digitalization. And I'm happy to have today representatives from industry and science who are willing to share their insights, ideas, and also recommendations. So first off, we have Professor Helge Stein. Helge, welcome. He's a professor for digital catalysis at chemistry at the Technical University of Munich in Germany, and he's working in the field of laboratory automation, machine learning for batteries and catalysis. His special interest is in engineering of science for horizontal and vertical integration. Welcome, Helge.
Hey.
Then we have Javier Olarte San Juan from CIC energiGUNE in Spain. There he's the technology transfer director. Welcome, Javier. Great to have you. And finally, we have Aldo D'Ambrosio. He's the battery cells segment leader and part of strategic marketing and solution management at COMAU, Italy. Hi, Aldo.
Good morning.
Okay, so again, we will first go through some general questions also to introduce our panel guests here, and then once again, just place your questions in the Q&A section of the teams here, and then we can go through them later on. Okay, so let's talk maybe first about how digitalization is actually a key element in the work of your field. So Helge, your work is centered around many approaches mentioned also in the position paper, for example, high throughput experimentation, machine learning, but also robotics. So how are these elements tied together in your field of work?
Well, so typically whenever you want to try to have a data-driven approach, you need to, well, there's very little data. In fact, we published a paper a couple of months ago for a machine learning model for early lifetime prediction. And one of the largest issues for us was to actually find data. So if you actually go into the web and you crawl everything, you maybe assemble about 1,000 cells. So we very often in academic research face the issue that we need to be able to acquire our own data and then make it publicly available, ideally. And this is for me at least, the main reason why we do automated kind of research. We build our own batteries, we make our own coatings, typically on a smaller scale than the pilot lines. But yeah, that's the main motivation. And then after essentially having done this for about 10-15 years now, we realized that it's nice to have something that can generate a lot of data if you cannot integrate it with data sources from across the room or across the continent. You're also lost. And this is then also why we are working very closely together with Simon and the team from SINTEF to also integrate ontologies in our workflows.
Okay, great. Another central concept that was touched upon in the position paper was advanced modeling and digital twins. Maybe a question to you, Aldo. How are these technological concepts part of your work at COMAU?
Yeah, it's at the starting point. Thanks for inviting me this panel session. I was hearing a lot of information that has been given as if placed on the table by all the presenter people. And I would just bring an example because I'm coming, I was yesterday and the day before at the battery show. And I think it's the right moment to show up this point. Everyone is really interested in selling machines. So what I've been seeing at the battery show, there are several potential customer and supply. So customers are asking for producing objects, producing batteries. And on the other side, there are machine builders like us that are interested to sell machines. So I've seen a very low level interest in these aspects that have been highlighted over here. So I really think that what you are doing, pushing this, is really important. And besides, so going to the point that you have been asking, Christoph, to me for the digital twins, we are actively and proactively working through, on one side, on a business approach. So to us, digital twin is fundamental because as machine owners, we must know how they do the job, okay, and how we can do and what we can do to close the loop, making them more efficient and avoiding the scraps. This is the first important aspect. The second one is that we participate in, for example, in a European project, it's BATWIN, where there are customers asking us.
Sorry, there's a microphone open that should be closed. Okay.
I don't think was a question. No, I'm sorry, Jack. Okay, so we are working actively on the European level because customers are asking us to put and introduce in our machine and pushing our machines on these digital twins, asking to machine builders like us to put the competence and the knowledge to take out and bring out of the machines all the potential, also through machine learning, artificial intelligence, to move those data that we have in thousands of tera, and actually we manage at a low level.
Helge, there's a first comment from your side.
Yeah, so how would you see it if, let's say, as you're a machine builder, that one would specifically ask all the machine builders, not just yourself, that there should be open standards in interacting with the machines. For instance, we now have OPC UA as a standard interface. To make that, let's say, even compulsory within either research projects or whatever projects funded by the European Commission.
We are as machine builder, I say, we are really in the middle of this very complex stream, as has been said by Mr. Maher before. We have the EPC, we have the operating gigafactories. In the end, we have the battery cells, and I think that we are really in the middle. I agree on the aspect of standardization. We are, for example, so I follow you when you talk about OPC UA. So we are really working on that. So we try to hear and benchmark what stays on the market. In the way we can also collaborate with machine builders to go in that direction. So I strongly agree with what you're saying.
Okay, great. So we're already touching upon a topic that we will also address a bit later on in terms of like how do we scale up this whole thing? How do we integrate all the stakeholders to actually working together here? But first of all, Javier, also to introduce you, you're working in the field of battery analysis. What are current data-driven approaches in the state of monitoring in your field that you're following here? Your microphone is still muted, I think. Yeah.
Okay. When talking about modeling data, when talking about modeling batteries, there are different techniques with advantages and disadvantages. Data-driven is one of those, and they have the ability to provide more realistic performance if you have the opportunity to gather the data on the real operation conditions that the battery is going to live for the lifetime. And this is one of the advantages. On the other hand, the disadvantage is that you have to spend a lot of time and money to gather all this information. But if you have the chance to do it, you are more likely to have the possibility to develop better accuracy estimators that will, at the end of the day, provide you more value on the utilization of your system. Yeah, basically.
Okay. Yeah, so there's a common scheme popping up here, which maybe we can address now also in the next round of questions, which is like the availability of data and also how all these stakeholders work together. So, Helge, current initiatives on providing common knowledge base and ontologies, for example, within BigMap, they are mostly focused around small fraction of data produced by research community. You also mentioned that your approach is actually to produce the data in-house by yourself because you just don't have enough data to work with. So what is, from your perspective, the outlook on the broader framework? How could these initiatives be scaled up and data made be more available, and how open are people also to data sharing actually?
So maybe a little bit the perspective from BigMap 1. So we have now the BigMap archive, essentially a data lake where, I think it's about 100 data sets that are now available, give or take a few more or less. And I think within the EU, that was, to the best of my knowledge, the largest open effort. I do understand that in this field, there's a little bit of hesitation to publish all the data, especially when it comes to let's say proprietary battery chemistries. There are approaches to share data whilst protecting intellectual property that are a little bit more complicated, but especially in the machine learning field, there's like federated learning and things like that. But I absolutely believe that at least maybe we should start with the academics and force them to actually publish all their data. Given all the different ERC grants of different levels, just tell everyone that is working batteries or any other field for that matter to actually make their data openly available. I think BigMap did do some solid groundwork, but we need to advance a little bit, and let's hope that I know there are different consortia that applied, but hopefully by I think in September or so we will know who is going to continue the work of BigMap. And we have some ideas, especially making this whole platform more open to the wider European community. And yeah, so there's a start, and this is what we need to do. To give an example from my own research, we actually then sometimes need to just team up with the industrial partners. We did that in the past with BASF as a large cathode material manufacturer, and they actually gave us under the umbrella of confidentiality access to all their data. We then trained machine learning models, actually made the models that were trained on their proprietary data not open, but only openly published models that were trained on openly available data. And I think that's a possible a way to go forward, to just have different tiered kind of models. But I absolutely do understand that some of the people also here in the audience might not want to share their data super openly, but we need to just find ways of protecting intellectual property whilst being as open as we can.
Okay, thanks. Another aspect is not just only having access to this data, but also creating all this data, and that would be maybe a question to Aldo and Javier. Concerning sensors and monitoring. So what do you think is actually the integration of all these sensors, the cost of all these sensors and the related infrastructures? How much is this a hurdle for your projects, and how much is this a critical factor? Maybe Aldo, if you first would like to start with this.
Yeah. If we think to if we look to the economics for a while of the impacts of potential application of sensors. So sensors are fantastic because we are in love a lot with them, because we use a lot of sensor. We are asked to use a lot of sensors. The approach that I think that has to be changed, especially working in an environment like this one for the batteries, in which we are changing our approach in terms of quantities. So we have been always working on body-in-white applications, so on automotive. Now going upstream, so the numbers is changing because we are working with quantities that are so we are talking about millions parts instead of talking about thousands. So the objective that also we are working on is to bring all these sensing systems upstream, so that much we can upstream. So if we go in deep in electric preparation, for example, to look close to the electrodes and to the potential that they have, and to the respect of the chemistries, for example, and the reactions that need to be need to happen in order to avoid, once you are downstream, to control something that is already closed and you cannot do nothing unless screwing it up, okay? Throwing up, sorry. And so I think that from our side, the impact of sensors is huge, but we have just to move them in the right position of the process, just to convince our customer that it is not important to look at them at the end, but the upstream is fundamental to also collect information and use them to make a redirection on an iteration on the process downstream.
So Aldo, no, Javier, Aldo was talking, I guess, more about the manufacturing side. I think you're more related to the operational side of batteries and analysis. So how much is there the sensor cost actually a factor, and how much is this a hurdle also for getting things implemented?
The cost of the sensor always has an impact on the performance of the overall system, but at the end of the day, industrially, the percentage of the BMS of the balance of the system as compared to the overall system is normally marginal. Of course, all the industry is working to have even more competitive costs, but the challenge is more to do with improving accuracy, not only of the sensor that will feed to the different BMS algorithms that will improve the accuracy of the estimators, which at the end of the day will improve the value of the utilization of the system. So it is important, but probably is not the big challenge. There are other challenges related to the sensors, which are to do with reliability, durability, and the possibility to have all these sensors able to live over the lifetime of the asset without necessity to do operational maintenance was related with calibration or fine-tuning, because this has an impact on the operational maintenance costs. So these are probably the challenges from the perspective of the sensors when talking about inoperando monitoring of batteries.
Okay, so now I would also like to give the audience the chance to ask some questions. So in the chat currently, I think there's no question that I see. So from the audience, curious to ask some questions to one of our three guests. Okay.
Yeah, I have one question. So the question is related to like how much of the like especially when it comes to state estimations, for example, in batteries, how much is the accuracy playing a role, especially when it comes to these kind of techniques? You know, like how accurate are we talking about, and what is the relationship with the data, etc.?
I guess this is for me.
Yeah.
When talking about the estimation of accuracy of the different state of capacity or health of safety, it is a very, very relevant issue. For instance, if we were dreaming of having a state of health accuracy of, say, something in the range of, say, 1%, 2%, or 3%, would be a dream for the industry, because 1 point of percentage on the error of the estimation of the battery has an impact on how much energy you have available. And when bringing this accuracy into the money and the valuation strategy of your asset, it comes down to how much money you put on the asset to have your service. If you have a 5% error, it means that you need to at least spend at least 5% more money in your asset to comply with your specifications. So the higher the accuracy, the better. In practice, today in industry, reaching SOH in the range of 1 or 2% is already a challenge. It is possible, but it's a challenge, and this has an impact on the system that you built, and the sensors, and the BMS, and the algorithms. But let's say the challenge is to target 1%. But you might find many systems in the market with accuracies in the range of 3, 4, 5, and even higher, which are very, very bad. But this is, I don't know if I answered your question. This is related to a state of health. Yeah. If we talk about the state of capacity, the issue is the same level of relevance, and the different standards in terms of accuracy are even worse on average. So there are very few real estimators that reach this level of accuracies. But this is the big challenge for the industry. And when talking about the state of power, the problem is similar. And when we talk about the state of safety, well, this is a new world where there are many open questions on how to measure the accuracy or the adequacy of your estimators in terms of safety, because it's a very wide, complex technique. It has to do not only with the cell, but with the electronics, the balance of the systems, and the protections, and the overall behavior of the operators of the system, and many other things. Yeah.
Maybe a follow-up question: what do you think is the biggest challenge, or what is the biggest lever we would need to pull to make those model more precise? Is it simply the quality of the data? Is it we need more complex models? Is it the embedding into whatever embedded electronics? What would you say is the largest source of error that someone need to overcome?
It is a mixture of many things, but if we to mention two, the accuracy of the sensors, of the voltage, current, and impedance, or temperature measurements has an impact, but the errors do come mostly from the difficulty to measure the evolution of the different degradation routes of the chemistries, depending on the use of cases. So it is not that easy to measure what is happening internally into the cell by only monitoring voltage, current, and temperature. And there are some positive ideas to work on in operando techniques based on impedance spectroscopy that will give you more detailed information on what is going on in operando in the cell over the lifetime. And that opens an interesting field of improvement in terms of models. Yeah. So both the devices and the algorithms, but most on the algorithms. But when we talk about the algorithms, the next point comes to the data that you have, and this brings us to the difficulty of this business, which is if you want to have a real accurate models, you need to be able to replicate the operational data of the cells of a given manufacturer with a given dispersion of manufacturability in a real operation condition that you are facing in the real life. And this is to do with temperature, pressure, C rates, the number of cycles, and so on and so forth. And then you will probably have the possibility to have accurate. If you do gather data in the different conditions, you are assuming risk of dispersing your estimations. I don't know. Yeah, basically, this is the challenge, which is a big one. Yeah? And this comes to the point of how we should be able to convince people to share data and to make public data from the experiments to help others and not repeat the experiments once and every time. Because this is one of the challenges that we have in this industry. There are many people doing the same in different conditions, but probably we don't share the knowledge.
I mean, now that we're here with BEPA, maybe that should be some call option that we that what one could do is we develop an infrastructure where independently people can train their models based on their data. You don't have to share data, but you share weights to let's say build a universal kind of SOX model that let's say the industrial community, but also maybe the research community could benefit from.
Yeah. This is a challenge. To my knowledge, there is an initiative at European level where the GRC has been doing quite interesting job on testing and sharing information with very many data from different manufacturers and chemistries. And I think this is the way of progressing in this. Yeah, we would be able to complement the testing result with methodologies or best practice or innovative ideas to develop hybrid models and so on. I think this is the challenge from not only for the scientific community, but for industry.
Yeah, that's great to hear. And actually, this was also one of the questions I was noting down. In general, like to see or to understand better how the different stakeholders are actually willing to work together. So Helge, you were mentioning that BASF, for example, you're working together already, so they definitely have an interest. Javier, maybe a question to you, like how open are the battery manufacturers to collaborate also when it comes to SOX monitoring or predictive diagnosis? How much willing is there to exchange the knowledge and actually progress together on this topic?
I think it's a difficult question because there is a trade-off in between being the best and gain the competitiveness against sharing knowledge for free and gathering information from it. So it's a difficult trade-off in between the interest of industry and the interest of a scientific community. Yeah, and many times. So to be honest, I don't have the answer to that. But to my knowledge, industry try to protect and gain advantage on what makes them better than the competitors, and this goes against from sharing knowledge from the communities. It's a big challenge, but I think to some level we need to find a way of improving this communication because the overall society will speed up, and we will, because at the end of the day, if we get the possibility to make our batteries long-lasting and get better performance over the lifetime, is going to be better for all of us. So we should raise the level of standards. When you talk to the cell manufacturers, you get some data, and they provide standard data. But this basic standard data that you get from the manufacturers many times is insufficient. Whether over time these cell manufacturers will be able to have more valuable information on the performance of the cells that will be delivered to the integrators of the cell users is good. But the problem with the chemistries of the batteries is that you need 10, 20 years to gain all this knowledge to provide this to the users of the cells. And this is the challenge.
Aldo, what is your take on this? Yeah, exactly. You already raised
I was trying to bring my small portion. Yeah. Again, we are in the middle because from one side we received a request from the cell manufacturer because we work on cell manufacturing, and so we are talking about tier 1, and we have to talk also with the OEMs who build the packs and the modules. What I see is that, from a cell manufacturer perspective, this approach on protecting chemistry brings us nowhere. But I think that the point is that they really don't know in the end how the cell will act once it will be in the modules and the pack, because it's something that at the moment belongs to the OEM. So this data sharing, I think it's really important because we need those information, because otherwise, once, for example, are in the stream of the cell formation, we just so our only objective is to respect the values that we received from the receipt of the customer, and we just test the cells in terms of internal resistance, impedance, and something like that. It's not enough. And once we are touching the cells, we should bring them, and should bring to the an advantage to the data that we put and we can share in terms of what happens if we charge in the wrong way the cell. And we don't do that. We use those data to bring an advantage only to ourselves as machine builders. So I think that this approach has to be changed to shorten, as was saying Javier, to shorten the time is required for having those data available and those products available as well.
Okay, are there any more questions from the audience? Please just open your microphone if you have a question. Well, maybe in the meantime, let's talk a bit more about the impact in the end of this whole digitalization and how this is going to transform the value chain. So, Helge, what do you think is the direct impact of this experiments you're doing, especially with with this high throughput experimentation and using robots and and machine learning, what is the effect on time to market, for example?
Well, the idea of or the premise of BigMap was actually to reduce the time to market, and if we are realistic, that is 30 to 40 years. The idea was to accelerate that by a factor of 10. I think, or at least show the capability of being able to accelerate this by a factor of 10. I think there are some findings in the BigMap project that made it, let's say, to market relatively fast. And for instance, formation and certain new salts and formulations, that was something that proliferated quite fast. I would really say within 2-3 years, and I believe there are soon going to be cells that you can buy that have technology that was in part developed by BigMap. I would maybe make a provocative statement. I would even assume that without any machine learning whatsoever, but simply by fully digitalizing your research, and it's not just digitalization. Digitalization is a tool and a prerequisite for integration. What is integration? That is essentially when I find something in my lab or anybody else. If we find something in the lab on some machine, that insight somehow needs to go to the next step. And what I at least feel used to be a problem is that going from, let's say, a coin cell, single layer, nice academic research where you, whatever, overfill the electrolyte, to go to just a single layer pouch cell, that might be relatively simple. Going to a multi-layer pouch cell is extremely hard. Going to multiple multi-layer pouch cells is extremely hard, and going even above that, like prismatic cells or so, I would say probably 99% or even more of the research findings on the very small scales die in the tracks. And what we need to do here is no longer just see it as we can do one thing very fast, but we need to integrate with the different levels. And then eventually also, and this is what I hope will now come more, is that we also get insights back, meaning really insights that we on the, let's say, academic research scale in few milliamp hours of capacity don't see. But we actually need to proliferate some insights back from the factories to academic research. And I think if we have, let's say, arrows pointing in both ways, we can get to a very nice equilibrium.
Sounds good. Aldo, from your perspective, what do you think, like for the implementation of digitalization in a factory, for example, or in a machine park? Like, does it make sense more if you think about scaling up to start with small experiments or with small machines and with high degree of customization, or is it better to roll it out on a broader level?
We should implement in both directions, so in all the three. So from the lab to the gigas. It's very obvious what I'm saying, but I think that it goes also with the concept that we were talking about before, accuracy and something like that. So we need to be the much we can accurate upstream. Check, control, verify if what has been developed, what is under development is good enough with the right level of performance. Then we should simplify the way we measure, but gathering much more information in terms of numbers of data as well as we grow with the scale of the process. Because, for example, at the pilot level, the objective of the customer is usually to be flexible, and at lower levels, so at lab ones, it's to be much more flexible. So they test several things, many things. Once you are at the giga level, you have one product that is produced million parts. So the objective is provide stability in the process once you are at the giga scale, and you have to confirm what we have been developing upstream. So my point is, we need digitalization at all the levels, but with different objectives. And as was saying Professor Helge, is we absolutely need this arrow going back from the gigafactories. And this actually doesn't happen because, yeah, on one side, we do not have in Europe enough. And on the other side, it's an approach of being protective on data that I don't think are too much needed to be protected.
Can I add something to Aldo's statement? Because I think it's absolutely right. I believe we have, on the y-axis, we have agility. Yeah. And then on the x-axis, we have, let's say, throughput or output.
Quantity, yes, exactly.
Yes, the quantity, exactly. It's, of course, in the research labs, we do the crazy things that where nothing needs to work, essentially. Then we have the pilot lines, and then we have the gigafactories. I would say from by the whole outset of pilot lines, it also has this like in the name already. Let's say there is that there are fast tracks from a pilot line to a gigafactory. I mean, this is essentially how the whole system that works. But what I believe what we have is we have a gap between academic research and the pilot lines. And we somehow need to bridge that gap with something, I don't know, like a pre-pilot line. And I see that quite often. We can scale up maybe to tens of grams. A few hundred grams is already quite a challenge for most academic research labs. But then really going above a kilo or maybe even 10, which most pilot lines need to have to just, start an industrially scale quota, that is extremely challenging.
Yeah, if I can add just last thing is, it's good what you say, and what we are experiencing is not exactly part of this panel, but we are doing a lot of jobs and activities with universities. We have in our company PhD guys and students and professors working with polytechnics, because for example, Fraunhofer Institute, we need to build the bridge. And we are building it, because if you have not correlation, which was university is doing, or on the other side, there are some questions that we do to the universities because there are requirements that comes from the customer. So fully agree on one side on the agility and quantity. I got these notes because I like a lot. I will bring to my colleagues this vision. And on the other side, the bridging that is actually really, really missing in the real world. Yeah. And the much we go downstream, and this is much more underlined.
Okay, so it's not just bridging gaps between pilot lines and small scale experiments, but also between the analog and the digital world. So taking notes is still a big thing. Very good. So it looks like we have some very productive panel session. There are also a few comments. Maybe you check them out in the chat. One pointing out to a similar discussion going on in our webinar that is going to happen on upcoming Tuesday. There's a link that Spiridon was posting. If you're interested in this topic, please follow this discussion there also. And then we had a comment from Peter Fischer that this could be also a topic for the Forschungsfertigung Batteriezelle FFB, which is a German scope project. So get into contact with Peter Fischer in case you're interested there. Maybe you can also post your contact data there in the chat. Okay, the panel session is drawing to a close. I would say some final questions from the audience. Last chance, if there are. That's not the case. Maybe a last round of questions in very few sentences. So what do you see as the biggest challenge from your field currently of work? And what is your suggestion to approach these challenges? Helge, maybe you want to start.
Sufficient funding at university research. No, and
I don't even know why I asked this question.
Yeah. No, we need a better cooperation, and also as academics, we need to go away from this view that we make something and then industry does it. We need to also accept the other way around.
Yeah. This pointing arrows in both directions, I think,
Yes.
was a common scheme we had here often. Yeah. Javier, what do you think?
Yeah, basically, in line with what has been said, I think we need to invest in robust data acquisition systems based on real applications on the available chemistries already in the market, with all the uncertainties from the manufacturers, material, and so on, and keep on working on improving the predictive methods, which is a lot of room for improvement from both for the sake of the industry.
Okay. Aldo,
Yeah.
what do you think?
Yeah, my last sentence is addressing the rising global demand for batteries while reducing raw material dependency. This is the huge and the big deal that we need to meet. Otherwise, there's no way.
Okay. So I would say we close the panel session here. Thank you for the discussion, our three guests here, Aldo, Helge, and Javier. And also thanks for the questions from the audience side. I see Adele, you have a last question.
Yeah, it's not so much a question. I'd like to invite you all back after coffee, because we're going to talk about hybridization, and we're going to link quite a few of the topics that have been talked about here into the real kind of implementation and the why we should do this. It's kind of answering some of the questions to what can this actually result in, and to the answers that digitalization can provide us with, the why. So I'm hoping you will join us. I think that we'll have a nice session with several presentations. So we hope to see you in 10 minutes time.
Yeah. And
Great.
before we close and go into the... Yeah,
is in this same link, or is it a different one?
It's in the same link, and I'm going to hand you back to Christopher, but he can see has something to add here.
Yeah,
Same
we
link.
just have some few closing remarks for Maher. Maybe you just want to wrap up the discussion and before we go into coffee break.
Right, sure. I mean, thanks for the panel. This was very interesting discussion, and then you brought really important points to focus on. My takeaway is this is an industry which is quite moving, still quite unstable. So when you have an industry and a technology which is stable, in general, you are linear, and you are linear only in one direction. So you do research, you bring the outcome of the research, you manufacture things, and then you bring it to the market. And that's linear only in one direction, one sense. We are here in an industry where we need a lot of return on experience, for example. We need a lot of feedback. You need to roll in, you need to roll out. So it should be two ways communication. This is one, between research and manufacturing, engineering, manufacturing, and then exploitation. And then you need as well to work with the research engineering departments within the companies who are in the batteries business. But also the universities out of these companies have to work very, very closely as well with these industrials. So there should be like a syndication of research and development and innovation. And there should be as well, more integration in the processes from R&D to manufacturing and so on. So these are the things where for this industry, we need to make it much, much better and much, much different as well than even, the closest industry would be automotive when you are manufacturing cars. But today, the manufacturing of fuel cars or thermal cars, this is proven that exists and so on. You don't need too much of what I'm saying here. But for the electric vehicles, for the batteries, this world needs a different way of collaboration, a lot of service level agreements in place, more skin in the games. So there should be as well more incentives across the whole value chain from research to the exploitation. And there should be also more thinking about, what are the sharing of, IPs, particularly in this industry, because they have to collaborate. If you put walls, people do not collaborate. You are happy because the IP is well clear where it is. But then at the end of the day, you don't have something very much innovative. And the last point is this digitalization is not like a cherry on the cake. It's in many companies now fully integrated in every business unit. So it's part of what everything is doing, what everybody is doing every day. So we need to think about it like to be fully integrated within the processes for manufacturing the batteries, for exploitation of the batteries, for recycling of the batteries. This should be everywhere here. And we have to think it that way. So it's a real revolution and a really different way of thinking that I haven't seen that much in other industries yet.